In this video, we're going to talk about work. Uh, Calculus was invented to solve actual physical problems. It wasn't invented for the sake of just interest in math. It was created to solve physics problems. And Isaac Newton, one of the two people that independently invented calculus, was interested in looking at problems related to gravity, planetary motion, optics, all kinds of things like that. And that's actually where the development of calculus came from. Work is one of these concepts that is a physics concept that is only easy to understand in the context of calculus. And so I want to talk about work in a couple of ways. First, I want to think about just the word work. In the plain English language, usually we think of work as kind of the amount of effort required to complete a task. And the definition in physics is actually quite similar. So in plain English, see if I can, good way to start this video off. Okay, in plain English, work is the amount of effort required to complete some task. In physics, the idea is fairly closely related. Again, if I can spell today. In physics, there we go. It involves the concept of force and distance, both of which you can kind of think of as related to the concept of effort. So work involves both force and distance, right? More force you can think of as more effort, and pushing something a longer distance, again, more effort. So those two concepts both are involved in the concept of work. Distance is a pretty straightforward concept that we've talked about a bunch in Calculus 1, probably. You know, it's something you have an intuitive idea of what it is, how far something is. Force, you probably also have an intuitive idea, but you may not have seen an actual definition of what force looks like in the context of physics. So I'm going to start off with the idea of force. So before we do work, let's talk about force a little bit more carefully. So what is force? Well, this was one of Newton's big concepts. Other than developing calculus, he basically developed a bunch of modern physics. So force, according to Newton's second law of motion, so Newton's second law of motion states that force is actually equal to a mass times an acceleration. So you've got an object that has a certain mass to it. The bigger the mass, the harder it's going to be to move, and you want to accelerate a certain speed. The faster you want to accelerate it, the more force that's going to be required. So that's the relationship here. Mass, again, we'll talk about the units of that in just a minute, but acceleration is a concept that we did talk about in Calculus 1. So if we want to tie this to calculus, we can think of force as being equal to mass times acceleration, where that acceleration is going to be the second derivative of some position function. So in this case, m is equal to a mass. It can be either in kilograms, if we're talking in metric, or It could be, if we're talking about imperial units, American units, it's actually a unit called a slug that you may not have heard of. X, we'll think of X as being sort of a function of time, and it's going to be our position or distance. And again, in metric, we'd probably measure that in maybe meters, whereas in imperial, we'd measure it in feet. And down at the bottom, we are taking the derivative with respect to time, so t is time. And in both metric and imperial, we would probably measure that in seconds in both cases. So force has these particular physical units. So in metric, I just want to mention what these units wind up being called. In metric, 1 kilogram meter per second squared, which is exactly the units you'd get multiplying through right here. So our mass is kilograms. Our acceleration, d squared x dt squared. We have the units of x in the numerator and the units of t squared in the denominator. So m, our meters, that's our position x, and t squared, that's our second squared down here. In metric, this has a nickname. We just call this a Newton. So it's equal to 1 Newton. And we just use the capital letter N for a Newton. And in imperial, we can write it this way. It's weird. We would never write it this way, but 1 slug times a foot per second squared is actually what's called, excuse me, a pound. So let me write out the word first. 1 pound. So even though we're a lot of times think of pounds as measuring a mass, what pounds actually measure is the amount of force that our body, when we step onto a scale, for example, it's the amount of force that our body is exerting down onto the scale due to the acceleration of gravity here on the surface of Earth. So that is the idea. So again, force in metric is a Newton, in imperial, it's a pound. This leads us to the concept of work. Now that we have an understanding of what force means, we can define work a little bit more carefully. So in the case of a constant acceleration and therefore a constant force, so if our acceleration and hence force, because we're going to assume that the mass isn't something that's changing, is constant, then work is just going to be the product of force and distance. It's literally force times distance. So writing that out, we simply have work, which we're going to just denote with a W, is equal to force times a distance. That's it. The units that we get mean we're going to take the units of force that we had up here and now multiply them by either a meter or by a foot, depending on whether we're dealing with metric or imperial units. So the names of the resulting units we get here are, in metric, 1 Newton times a meter is just what we call 1 Newton meter. It's also a term that you may have heard if you've taken physics classes that has a nickname, and that nickname is a joule. So 1 Newton meter is 1 joule. And that's used oftentimes to measure energy. It turns out energy and work share the same units. In imperial, instead we get 1. The order that we do things here is not super important, but it's just a convention that's picked. When we're talking about work, we write it as a foot pound in that order. Foot first and pound second. Pound feet, you may have recognized from like a car commercial, is typically used when referring to torque. Technically, they are, again, kind of the same measurement. They just show up in different contexts. And a lot of times when you talk about torque, it's actually a vector quantity as opposed to a scalar quantity. There's a direction associated with it. So I'm not going to go into those details, but we have 1 foot-pound. I'll just write that out. 1 foot-pound. And if you want to do the conversion, I'm not going to go through the conversion, but it turns out these numbers aren't actually all that far off. A Newton meter relative to a foot-pound, the conversion factor is as follows. 1 foot-pound is about, so let me make sure that it's totally clear these are, got it, that these are approximation symbols here. It's about 1.36 joules. So 1 foot-pound is 1.36 joules or 1.36 Newton meters. So these are what the units are going to look like. So how can we put this idea of work to use? Well, there's going to be a couple of different types of problems where this gets put into context. So one of those contexts is gravity. Same thing that Newton was working on when he developed all of this. So let me write this out a little more cleanly. It's going to have to be good enough. So for example, how much work is done if we want to lift a big rock up a certain height? So this will be a really straightforward example. How much work is done against gravity in lifting a big, heavy, let's say a 200 kilogram rock three meters into the air. Well, because we're presumably working directly in a straight line against gravity, work is just going to be force times distance. We already know that based on a couple of factors I'm going to give you, we know the distance right off the bat. The distance is going to be 3 meters. So now we just need to figure out the force. To figure out the force, we take our mass. Come back here to the definition of force. There we go. We're going to take our mass and multiply by the acceleration due to gravity. So I'm looking at my F equals ma formula up here to get the force that we need. So our force is going to be the mass, which is 200 kilograms, times the acceleration due to Earth's gravity. And it turns out that is 9.8 meters per second squared. How do I know this? Where am I getting this number? If you take a physics class, you'll become acquainted with this number very quickly. So let me make it clear. That's a multiplication symbol that we've got going here. So this is our mass. This is the acceleration due to gravity. And these two pieces together give me my force. And we still need to take care of the distance. So the distance is going to be times that additional 3 meters. So this is our distance. And this is the piece that gives us the D in our work equals F times D formula. So if we multiply all of these together, we wind up, and just doing this in the calculator real quickly, wind up, I got 5880. And what are my units? Well, we can actually look at all of these, but at the end of the day, what we care about is the units of force. These two units combined, kilograms, meters per second squared. Kilogram meter per second squared is what we called a Newton. And over here, the distance in meters, this is a Newton meter. So we could write it as Newton meter, or if you prefer, you can use joules, which is symbolized with just a capital J. So just to be clear, the symbol for joules is just a capital J. Okay, so that's easy. This isn't even a calculus problem really at all. This is, can you multiply, 3 numbers together? And it's so easy because in this particular case, the acceleration due to gravity is a constant. The acceleration is constant, therefore the force is a constant. We're moving in a straight line, so that's a constant, and it makes it a really easy problem. But what if the force is variable? What if it changes? So let's think about what we would do in this case. So if we're going to move this same object, and we're going to still move it in a straight line, but the force that we're applying is constantly changing for some reason. Maybe we're pushing an object just in a straight line, but it's really windy, and the wind is kind of whipping up, and when the wind blows hard, it's harder to push, and when the wind blows less hard, it's easier to push, and therefore our force is variable. Something like that. How would we deal with that situation? So let me write this down. If our force is variable, but the object is still moved in a straight line, so if an object is moved in a straight line, so we don't have to worry about dealing with D right now. It's still going to just be a constant. But if it's done by a continuously variable force, so let's make sure that the function that we're going to use to describe how the force is varying, that it's a continuous function. So by a continuously varying force, let's call that force f of x. So it varies based on whatever position we're at. Then in this case, the work done in moving the object from some starting point, which we'll call x equals a, to some endpoint x equals b. So in moving the object from some starting point x equals a to some ending point x equals b is given by the following. That work is going to be, if you think about it, we're going to kind of chop up the amount of work you're doing, and instead of talking about taking this whole big long distance from A to B, how much force are you doing for like the first inch? How much force is required the next inch? How much force is required the next inch after that? And sort of chop up our moving of this object into a bunch of little segments, add up all those pieces of work required for each little segment of movement, and we wind up with an integral. So it's going to be the limit as n goes to infinity of the sum of basically what was the force on that first inch. So that first inch maybe we would write as x sub I stars, that's somewhere on that increment that's the first inch, times the delta x, which was the 1 inch we had to move. And we're going to do that for each inch along the way. And in this case, we'll take the limit as n goes to infinity. So after inches, we'll be using tenths of inches, and then smaller and smaller and smaller. If we're doing it in meters, we'll go from chop it up into centimeters and then millimeters and so on and so forth, all the way down to nanometers, and take the limit again as n goes to infinity. What do we wind up with? This is our limit definition of an integral. So it's the integral from a to b of f of x dx. All we need to integrate is force with respect to distance. This is our distance, so here's our force. Remember, dx has units. It's a little tiny bit of distance in this case. So here we're adding up a bunch of forces times distances, and we wind up with this whole thing giving us the units of work that we're looking for. So just keep that in mind. Another context that this might show up in that kind of relates to some of this is, instead of talking about gravity, what if we did springs? Force due to a spring. And this is going to involve something that you may have seen if you've taken physics called Hooke's law. And you will see this again down the line if you take differential equations, which is actually a class I will be teaching in the spring. And Calc 2 is the prerequisite for it. So if you want to take differential equations in the spring, it's a really interesting class. It applies, it's really application focused. And this is one of the concepts that comes up in there in a lot more detail. Okay, so in this case now we're going to be talking about work related to springs, and therefore forces related to stretching or compressing a spring. So it turns out, according to Hooke's law, that the force required to either stretch or compress a spring it turns out that this is not constant, right? If you think about any spring that you've ever actually held in your hand, it tends to be easy to compress it just a little bit, but it's really hard to compress it a lot. Similarly, you can stretch it a little bit, but it's really hard to stretch it a lot. And the idea is that the force required is going to basically be proportional to the amount, to the distance or the displacement of the amount of stretching or compressing that you've already done. So in this case, the force required to stretch or compress a spring is proportional to the distance that it is currently displaced. From what we would call its equilibrium position, or its sort of natural length. Right, so this works in both the stretching direction and the compressing direction. What this means is that in this particular case, the force, and this is what Hooke's law is, the force is equal to something times this displacement d. And the letter we're going to use is k. There's a constant of proportionality times d, where d is the amount that this spring has been stretched or compressed. So in this case, let me write these down. K, this constant of proportionality, is what's called the spring constant. Oops, spring constant. And obviously, different springs have different difficulties with stretching or compressing them. If you're getting a spring out of a watch, it's going to be pretty easy for you to just stretch or compress it using your fingers. But if you're talking about the spring, on the suspension of your car, that's going to require a lot more force to either stretch or compress the exact same distance as your little watch spring. That's what the K is related to. How hard or easy is the spring to stretch or compress? So that's K, it's our spring constant, and D is two separate words. Basically the displacement or the distance that the string has been stretched or compressed. Okay. So let's do an example of a problem related to these, which is also something you will likely encounter on your homework. Okay, so let's say that a force of 30 pounds is enough to compress a spring 5 inches from its natural length. So maybe it originally starts off as 20 inches. So in this case, a force of 30 pounds compresses a spring by 5 inches. So 5 inches from its natural length of 20 inches. Okay, so here's what we've got. I want to figure out the amount of work that's required to compress that same spring 8 inches. So let's do a couple of parts. Find the work. Required to compress the spring 8 inches. So obviously, just quick sanity check. If 30 pounds compresses it by 5 inches, the amount of force required to compress it 8 inches is going to be more than 30 pounds. So keep that in mind. It's going to be more force that has to be applied to compress this thing 8 inches. So basically, our starting point is Hooke's law, F equals KD. So if we start with F equals KD, if we look at the information that's given, what's given is a force, 30 pounds, and they give us a distance that it's been stretched or compressed in this case. So they said it's been compressed 5 inches. They give us F, they give us D, and we need to use that to figure out what the spring constant is of this particular spring. Once we know the spring constant, then we can apply different distances to that spring constant to get different forces. So the whole point is we need to find K first. We need to find that spring constant. It's the one piece of information that's not given in this problem. So we are given that 30 pounds of force should be equal to our spring constant times the amount of displacement that just occurred, which was 5 inches. And if we think about what's required, it's given in inches. We can do things in terms of inches, but ultimately I want to stick to the more common units where we involve feet. So just keep in mind, I want to convert from inches to feet here. So because this is likely what they'll ask you to do on a homework. So 5 inches, we can just write that as a fraction. That's equal to just 5/12 of a foot, right? 5 out of the 12 inches of a foot. So we can just even keep it written as a fraction. And now we want to solve for k. So I have 30 pounds equals k times 5/12 of a foot. We want to divide by 5/12 feet, or similarly just multiply by 12/5 with the units of inverse feet. And we wind up getting that k is going to be equal to, so 30 pounds, I'm going to think of it as a multiplication, times 12/5 with units of 1/feet, right? The fraction gets inverted, or we take the reciprocal, but so do the units. And we wind up with, out of this, we can do a little simplification here, cancel this, that's 6. We wind up with, in this case, 72 pounds over feet. And that is our spring constant here. Once we have our spring constant, we can use that to actually compute some work now. So we have our spring constant, we have this force that we've ultimately figured out how to now compute for other distances. And now what we need to do is compute the total work required to compress the spring. So there's a lot of steps involved here. Let's think about what we've done so far. We've found the spring constant that's going to allow us to solve for the different forces at different levels of compression on this spring. Now we need to use that to figure out the work required to compress a spring 8 total inches. So we started with force. Once we have force, we know that force times distance, or in the case, because this force is no longer constant, we're going to have to use this equation up here. If we integrate that force over the distance that we're talking about, we will be able to compute the work that we're interested in. So now that we have a varying expression for the force by finding that spring constant, our variable expression is that our force is going to be the spring constant, 72 pounds over feet times the distance of displacement. There we go. We can compute work. Okay. So, how do we compute the work? Well, we just saw that the work is going to be an integral in general from a to b of f of x dx. That's it. We need our expression for our f of x, and we need to figure out what the a and the b should be. So, in this particular case, we just talked about our force. We need to convert this into an f of x. This piece over here is our f of x. So how do we relate it? We need it to be a function of x. Over here I have it written as d. But if we think about our spring as putting it on an axis somewhere, so let's imagine that this is it. Maybe this is our x-axis. And the natural length of the spring we said is 20 inches. So maybe we want to do, imagine it's going along this way, and there is the 20 inches, and we want to compress it. We can fix the right end and compress from the left. We can fix the left end, compress from the right. mathematically it won't matter. So I'm going to make it easier, fix it on the right side, and think about this position over here as being the thing that we can move. So we can move it in the positive x direction to compress this spring. So for us, I want to move this thing according to the following. If I were to move it to here, to this point, and we call this point x, the distance that we would have compressed it, d, would be equal to x. And so in this case, I can treat this d here as just x. We're fixing it on this side. So imagine that this side is on a brick wall, and this is the side that we're moving. We're compressing from this side. And now the way that I've got it set up, you pick the x value. If we only compress it to here, like an inch, then x would be 1. If we compress it 5 inches, x is 5. If we compress it 8 inches, x is 8. So the distance that we compress it is just whatever the x coordinate is that we wind up with. So that means that my f of x is just going to be 72 times x. We'll worry about the units in a minute. Let's just do the math. 72x. And there's my dx. So this is my, again, here's the force. Here's a little tiny distance. And we need to figure out how far we've compressed this. It's not 0 to 8. We didn't start with 0 inches of compression, go all the way to 8. Or sorry, we did start with 0 inches of compression, go all the way to 8 inches of compression. But we're not using inches. We're using feet. So we need to convert that to feet as well. So we're going to start at 0, and instead of going to 8, we're going to 8 inches, which is 8/12 of a foot. So this is what our formula looks like. We compute our integral, and we get that the integral of this is going to be 36x squared, evaluated between 0 and 8/12, which you can simplify to be 2/3, make life a little bit easier. And we'll plug that in, 36 times 2/3 squared. I don't need to worry about the lower bound. When I plug in 0, it's not going to give me any contribution. So I guess I can write that if we want. It's going to be minus 0. This is going to be 36 times, what am I going to get? 4/9. And we can do some cancellation. I can cancel the 9 on bottom with 36 and be left with just a factor of 4. And that gives me, in this case, 16. Think of what the units all were. Over here, we have a force times a distance, so our newtons times our meters, but in this case we're not using newtons and meters, we're not doing metric. This is going to be in pounds, this is going to be in feet. So we've got our, in this case, to make sure that we're keeping everything on track, this is our units. We got foot times pounds. That is the amount of work done. At the end of the day, this is just a multiplication, so if you ever write pound times feet instead, I won't take off points for that. It's really just a convention that typically when we are talking about moving something in a straight line, you do foot times pounds. If you're talking about torque, which has to do with rotation, you typically use pounds times feet. But ultimately, the units have an equivalence, so I'm not going to take off if you write pound feet instead of foot pounds. So just keep that in mind. Okay, so that was a lot of work for this one little problem, but not once you see it done once, it's not that difficult. How much work would it require to do the same thing? So I don't want to solve another integral, but like, let's just set up the integral. So let's set up the integral giving the work required to compress from 8 inches down to 10 inches. So the required work to compress from 8 to 10 inches. Okay, Keep it all on the same page here. Okay. So it's the same spring. We haven't done anything. All that's changed in this case is the bounds of integration, right? We're still computing work with the same formula. The force still varies, and the force still varies according to this formula. The spring constant hasn't changed, so it's just going to be 72 times x. So our integral for our work in this case is the integral of 72x dx. The only thing that changes is instead of going from 0 to 8 inches, we're now going from 8 to 10 inches. So that's going to be from 8/12 of a foot to 10/12 of a foot. And that's the only thing that would change. So just keep that in mind. Once you've done it once, you've found that spring constant, you've got the integrand set up, you can apply this with other conditions put on of other things that we're trying to do to this. And it's not that hard to figure out the sort of the rest of the problem. Okay. Let's do maybe one more of these. Let's talk about the work involved not in springs, but dealing with liquids. I want to pump some liquid. So as another example, not a spring one this time, let's imagine that we've got mercury held in a big tank. So mercury is held in a large tank. Let me take away large. I don't know how big I'm going to make this tank. It's held in a tank shaped like an inverted, sorry for my handwriting, I'm still getting used to this new tablet thing that I've got here. An inverted cone with, let's say, the radius of 2 meters and height of 5 meters. If there's 4 meters of mercury in the tank, I want to find how much work it'll take to remove it all up through the top. Let's say all through, oh, come on here, undo. So maybe the opening of this tank is at the top. So we've got to pump it out of the top to get it out. So even if we can get this thing started, and even using like siphoning effects, this is always something that somebody brings up in class. Even if we're doing siphoning, all we are doing in that case is using gravity to be the thing that applies the work, but it's still the same amount of work to remove this liquid out through the top, even if you can use siphon action. It's just that you might not be doing that work, gravity would be doing the work. But overall, it's still, we're not interested in who's doing the work, we just want to know how much work is required, regardless of who or what is accomplishing that work. So keep that in mind. We are just trying to basically lift all of this liquid out of the top of the tank. That is ultimately the goal. So let me draw a picture so we can get a sense of kind of what we're dealing with here. So it's going to be a cone. And that cone, I said, has a radius of 2 meters up here at the top. So that's going to be 2 meters. I'm going to say, I think I said it had a height of 5 meters. Yes, a height of 5 meters. Let me try this again. I want to make this a little better. Okay, good enough. Oh, I can live with this. Almost live with this. Okay. There we go. So let me just put some axes on here to give us some reference points. We've got our x and y axis. We know that this thing is filled up to initially a height of 4 meters. So maybe that's where the initial height up there is filled up to there. So this height right here, even though the total height to right here, so there's the 2 meters. Let's make this clear. This height is 5 meters, but this height is only 4 meters. Give myself some more room here. So 4 meters for that height, 5 meters for that height. Okay, so we want to get this all out the top of the tank. Here's what we need to think about. We're going to need a little bit of information. I need to give us some information about the density of mercury in a little bit so we can know how heavy it is, so we can figure out what the force is required to sort of work against gravity and lifting it up. We need to keep in mind that there's more of the liquid at the top that doesn't have to travel very far. There's less of the liquid down here near the bottom that needs to travel the full 5 meters before we can lift it out of the tank. And so this means that we have a lot of moving parts in this problem. So let's imagine that I just want to move one little slice out of the tank, and let's put it up at this arbitrary height right here. So I'm going to imagine that this is the slice of mercury, and I'm drawing it as a disk. This is the slice that I want to move up out of the tank. How far? So first of all, where is this? And second of all, how far does it need to be moved to get it out of the tank? So let me look at these two distances. So that's our little slice that I want to pull up out of the tank. The way that I've drawn things, that slice is going to be occurring at a height of y. I'm going to just call this distance y, whatever the height is. Down here, y would be 0. Up here, y is 5. This is somewhere clearly in between, bigger than 0, less than even the 4, so it's somewhere in there. This is just the y coordinate. This is the distance that it needs to travel for us to get it out of the tank. So this is the d of y that we're going to wind up using. It's going to be a distance that is variable. What is that distance? Well, in this case, if the slice of liquid that we're trying to move out is at a height of y, then the remaining distance to the top of the tank should be the height of the tank minus however high it already is. So it's going to be 5 meters minus the current y coordinate. So this is going to be 5 minus y. So that's going to be the distance that we need to move it. We now need to figure out how much liquid is sitting here in this little slice that we're looking at. So that's going to, again, vary. Up here near the top, the radius of this little slice would be bigger. We'd have more of the mercury up here near the top of the tank. And down here, the slice would have a really tiny radius. We'd have very small amounts of mercury down near the bottom. So not only is the distance that we need to move it going to vary from the top to the bottom of the tank, but so is the amount of force, because this is going to be a heavier slice than one that would occur down here, but it's going to be a lighter slice than one that would occur up here because it's in between. We know that the force should be related to the mass of the liquid that we're trying to move. So I want to think of it as basically, I want to figure out the total force required. So we've found our distance. How much force is required to move this slice? to counteract gravity on this thing? Well, there's a lot that goes into this. So again, remember, force is going to be mass times acceleration. And that means that I need to find the mass of that little section and then multiply it. So this is our mass. And then this, in this case, is just going to be the acceleration due to gravity. So we've got our mass, we've got our acceleration due to gravity. I already know the acceleration due to gravity. We're doing this all in metric, so this is going to be that same 9.8 meters per second squared that we saw earlier. So the acceleration is taken care of. We need to figure out the mass. So how do I find the mass of this little slice? Okay, so in our picture, whoa. Let's get this back. Good enough. I want to draw a couple more pictures here. Here's what we're dealing with right now. This is the slice that we're talking about. It's going to have a little tiny thickness. Our delta y, because it's a change in the y direction. And it has some radius here, r, and the density of mercury, so the mass is going to be equal to the volume times the density. And it turns out the density for mercury is 13,593 kilograms per cubic meter. So that's the density. It's very heavy stuff. This is just a number that I think they have it in our textbook. You can look it up on Wikipedia, whatever. But that's the idea. So density tells us how much mass is there to something per volume, right? The units are mass over volume. And so when I multiply it by a volume, this V here, it'll cancel with this and we will get units of just mass. And that's ultimately what we want, right? We want mass. So this has units of, right, this is mass, and this has units of mass, sorry, volume. What am I doing? Oh, come on, undo button. What did I say here? This has units of volume, and this has units of mass divided by volume. And when we multiply them together, the volumes will cancel and we'll just wind up with the mass that we're going for. Okay, so we just need to figure out the volume. What is the volume of this region? Well, we talked about this in some previous videos. It's just the volume of this little disk. That is going to be the area of the base, so pi r squared times our delta y. So this piece here is going to be pi r squared times our delta y, and we're multiplying that by this density. However, the equation that we're going to be doing to compute work is going to be an integral. We can already see that our distance function is a function of y. Our small parameter is a function of y. This is going to wind up being our dy. So I need this volume to be entirely in terms of y. I can't use r here. And notice the r does vary from the top to the bottom. So we need to figure out what that radius is. As a function of y. And we can do that by looking at the picture of our tank. I want to figure out what the radius is for a given height. If we just draw the cross section of our tank, it's just a triangle. Right, here it is from the side. This is the side view of our tank. Here's X, here's Y. I know that at the very top, that's 2 meters, whereas this distance right here is 5 meters. And I'm asking, what is this R at a height of, we just said we're calling this Y. And I can just use the fact that these two triangles are similar triangles. They have the same ratio of their horizontal side to their vertical side. So I know, so use similar triangles. This is the easiest way. There's other ways, but this is much easier. So I'm using the fact that we've got similar triangles. 2 is to 5 as R is to Y. And therefore I can solve for what R is. The radius of this is just going to be multiply both sides by Y. It's 2/5 Y. So what I'm suggesting is, however high up you've gone in the tank to some Y coordinate, the radius at that point is going to be 2/5 of the total height that you've gone up, because that's the ratio of the radius to the height of the tank itself. And we're just using similar triangles. Okay, so let's put this whole mess together. Let's put it all together. See if I can write it in a complete sentence. Let's put it all together. Okay, so let's find the work. The work, if we'll recall, is going to be basically the force times the distance, and we need to sum all of these up. So I'm going to do our limit as n goes to infinity of the sum from I equals 1 to n of our force times our distance. We'll just call it d of xi, whatever that distance looks like. This looks similar to what we talked about earlier. I just want to show how we derive the integral in this. In general, you don't need to do this step. If you're doing your own calculations, we can jump to an integral. But I think this illustrates the pieces that are going to go into all of this. Okay, so we've been putting a lot of work onto this force. We also already have an expression for this distance. So if you'll recall, the distance, this was, oops, and I'm using x's. I should be writing with, let me change those to y's real quickly here. We're doing it vertically, so I should be using y's instead of x's. Okay, this was 5 minus y. That was the distance that everything needed to move. And again, where am I getting that? That is just coming from, boom, that expression right there. That's the distance that everything needs to be pulled out. And now we're working on this force piece, which is going to be the culmination of all the effort we just put into everything here, right? So the force is going to be mass times acceleration. We know the acceleration due to gravity is 9.8 meters per second squared. To find the mass is going to be the volume times the density. I've given you the density. And now we've got the volume. The volume is pi r squared times this little delta y, where the r is now given in terms of y as this piece here. So I'm going to use all of these pieces to work our way up to this force. So that is what this piece is. So this piece is our big complicated force that we just took a bunch of steps to get to. So let's keep this in mind. The force, our F of y, and I'll just write it as F of y. I'm going to drop the little, the I index and the star just to make life easier as we write this. Doesn't really matter. I guess whatever. Excuse me. Okay, so F of y sub I star is going to be the mass times the acceleration, which is going to be 9.8 meters per second squared. And that mass is going to be the volume times the density. The density I said was 13,593. So, oops, with units of kilograms per meter cubed times the 9.8 meters per second squared. And our volume is going to be equal to pi r squared, where r is, we just solved for r, 2/5 of the y. So pi times 2/5 of y squared. So there's my pi r squared times my thickness, delta y, times my 13,593 kilograms per meter cubed times my 9.8 meters per second squared. We put this whole mess together. So what I'm going to do is I'm going to multiply this number times this number times the square of this number. And when we do all of that, I wind up with, let's see here, something in the ballpark of 53,284.6-ish, I guess, once I've factored all these in. 0.6 pi times, we've got our y squared. So that's this number right here. This number is this number, this number, this number, and this number, all multiplied together. The 2/5 squared, rather. What's left? Well, we still have a y squared and a delta y. So, putting these pieces together. I'm going to get that the work is the sum. It's the limit of the sum, rather. Limit as n goes to infinity of the sum from I equals 1 to n of this number that we just found times my yi. So 53,284.6 pi, the yi star squared times the 5 minus yi star, whatever that value is, times the delta y. And if we convert this now to an integral, and forget about all these crazy limits, what we've really wind up with in this particular case is the integral of 53,284.6 pi times y squared times 5 minus y dy. And we need to figure out the bounds of integration. Well, what liquid are we trying to remove from this thing? Right. Notice I put my origin down here at the bottom. I'm trying to remove everything from down here at a height of y equals 0 up to where it was filled. And the height that it was filled to was 4 meters. So I'm integrating from 0 to 4. If you look in the book and follow their example, they actually put their origin, instead of having their origin down here at the tip, they put their origin up here. You can read through their approach, and if you like that approach better, it leads to the same result, but you can do a problem that way instead. And just as a heads up, as I do all of these examples, I try to make my examples different than the examples that are in the book, just so that you have a second example to go reference if you want to read the book as well. Okay, so here is this big mess of an example, and again, the result of this will ultimately be units of Newton meters. You can compute this integral if you'd like. I'm not even going to bother. I just want to set this integral up, and ultimately on an exam, if you had a problem like this, even if I did ask you for the answer, if this problem was worth 20 points or something like that, just setting up the integral correctly would probably be worth, 16, 17 of those points. That's the hard part. Setting up the integral is the hard part. I won't care so much if you get the exact right answer at the very end of the problem. At least not a lot. You won't have a ton of points for that. So this is where the whole thing comes from. And just keep in mind, this piece right here, this piece is the distance that we're moving stuff. And the rest of this, that part, and this part, they have to do with the force. Right? This is our little tiny thickness of the force that we computed by taking basically the volume along with the density to get the mass, along with the acceleration to get the force. But this dy is part of that volume that we use to compute the force. And lastly, this part over here, oh come on, so I'll do in a, let's just erase this, oh come on, there we go. This part over here just tells us, what are we moving? Right, so we're moving 4 meters worth of that, 4 meters deep worth of that mercury out. So this is what our result looks like. And in general, this is kind of how you can set up one of these problems. You don't have to do it from scratch. As long as you can figure out the distance and you can figure out the force, we're just integrating the force times the distance. That's really what we're doing. Adding up all these force times distances to get one big work. Okay, hopefully that makes some sense. Let me know if you have any questions, and otherwise, see you in the next video.